We're going to run through the first lecture for abstract algebra. This is going to be an introductory kind of lecture. We're going to review some of the preliminaries that are hopefully known to you coming into this course. If not, it'll be good for us to at least make sure we're on the same page. To start with, I'm going to review some of the common symbols and shorthand that we will use throughout this course. These are fairly standard, but you might have seen slightly different versions or slightly different shorthand depending on your professor for previous courses, so I just want to go through this to make sure we're all on the same page. So to start with, the one that's going to be particularly helpful to us for proofs is you're going to see an arrow-looking symbol like so. This means implies. So if the statement on the left, A implies B, then we would say A implies B with this arrow here. It's particularly helpful because when we go to the next step, we don't want any ambiguity about where we're going step by step in our chain of statements. Likewise, if you're trying to be careful, you might see something like A does not imply B. In this case, trying to be careful about when you can make certain assumptions. It might be the case that A sometimes is true and B is true, but if it's not true in general, I might say something like A does not imply B, just so we're very careful to not generalize unduly. If you see something like this, A and B imply each other, this means A and B are logically equivalent. Now, if we're thinking in the same vein, you might think about the IFF being if and only if. If and only if, logically equivalent, kind of appear in the same places, right? If you want to say something is true if and only if another thing is true, that might be shown the same way as the double arrows. And depending on if I'm writing it in sentence form, you might say the if and only if, but in the process of using mathematical symbolism in a proof, I might use the arrows instead. And finally, if I'm trying to show something as a contradiction, I will use these two arrows facing in towards each other to mean contradiction. I might state something like A and B contradict each other this way. Or you might see something like statement P exclamation point, and this means P is a contradiction. Now I'll try to be clear to state it's a contradiction afterwards, but if you see an exclamation point in a proof like that, I'll only use that when I'm making note of a contradictory statement. So some other shorthand that's pretty common. ST means such that. When you're writing sentences, it's just easier to use the shorthand when writing a proof. Upside down A means for all. Backwards E means there exists. And if I'm about to start a proof, I will say PF for proof typically. Or if I'm going to give an example of a particular definition, I might say EX for example. At the start of a proof, I might use shorthand like WTS for want to show, or NTS for need to show. This is particularly helpful if we want to show multiple things. We might say, here's what we want to show out of the statements given these things, and by organizing your thoughts at the beginning of the proof, it makes it easier to kind of go through the rest. So in lecture, I might use this kind of shorthand, but it's not strictly necessary in every proof we do. At the end of a proof, we will typically see something like a square that's empty, a boxed-in square, or a QED. This basically means end of proof. You've shown what you needed to show. Now the other shorthand we're going to use are going to be some common sets of numbers. We'll use these throughout the course quite a few times. So when we're working with our natural numbers, I'm going to use kind of this bold script N. And for our natural numbers, we're going to make the assumption that it includes 0, because when we're working with our modular arithmetic and those kinds of things, we do need to include 0, so it's much more convenient just to throw in 0 here. We will also see Q and Z, Z being our integers, Q being our rationals. We will see our bold R here, this is the real numbers. And we'll see this C with the line, this will be our complex numbers. As linear algebra is a prerequisite for this course, you might see something like Rn to be n-dimensional real space. Man, I can't spell. This is going to be like a vector with n real entries. You might see something like Rn by m. This is going to be n by m real matrices. And if you see something analogous for Q, you might say Qn. This is just going to be n-dimensional rational space. So instead of having real numbers, you're going to have rational numbers instead in your vector. And you can do something similar for integers if you're using superscripts, although we'll be careful with that. You can do something similar with natural numbers if you want to, and we'll talk more about this with sets and Cartesian products. The other common shorthand you're going to see is you might see something like R plus, and this plus in here implies positive. So this would be the positive reals. And likewise, you could do something like Z plus for positive integers. Note that this does not include 0. So it's another reason why it's helpful to have a distinct symbol n for including 0, and then Z plus when we don't want 0. If the natural numbers were just the same as the positive integers, then it'd be kind of silly to not just use Z plus the whole time. So with that in mind, I'd also like to review some common proof methods that you will see throughout this course, and you will find helpful for various homework, test questions, and group activities. Really, there's 4 main proof methods you're going to see. You might have to use a combination of these for proving statements, but you might have a direct proof. You might have a proof by contrapositive. You might have a proof by contradiction. Or you might have a proof by induction. So we'll go through, give you a quick definition of each one of these things as a refresher, and then we'll do an example of each. So for direct proof, what you're going to do is you're going to show a statement follows from the given assumptions by a chain of implications. So, for example, suppose we know that 3x plus 2 is even. I claim that this implies x is even. So if we want to prove this, we might use direct proof. We could say, well, 3x plus 2, we're going to call this a new number. Maybe we'll call this equal to y. We can subtract 2 from both sides. 3x plus, 3x equals y minus 2. And we know that y is even, so we could also write this as something like 2m for some integer, because we know that y is even. So we could say we have 2m minus 2, giving us that 3x is really equal to 2 times m minus 1. Notice that this implies 3x is even, and because we're assuming that y is an integer, x is an integer here, then we know that x is equal to 2. m minus 1 divided by 3. We can bring this 3 in. We can say we have 2 times m divided by 3 minus 1 divided by 3, or we could say minus 1 up here. But either way, because we're operating under the assumption that m minus 1 over 3 is still an integer, then we know then that x must be even. So thus completes our proof. If we were to state this problem in the homework, we'd probably be a little bit more careful to state that this is a even integer, and we're going to assume that x is an even integer. We're assuming some stuff about divisibility here we kind of glossed over, but if we're assuming x is an integer before we do this, then we could make that claim. Now, what if we want to do a proof by contrapositive instead? Well, recall that the contrapositive takes the original statement, P implies Q, and it gives us the logically equivalent contrapositive, which is the negation of Q implies the negation of P. So, for example, if we look at the statement we had above, our statement was 3x plus 2 is an even integer, therefore x is an even integer, right? So what if we instead say x is an odd integer? Then we claim that this implies that if x is odd, then 3x plus 2 is an odd integer as well. That would be the contrapositive, and the claim is that this is logically equivalent to the original thing we were asked to prove. So if we're doing a proof by contrapositive, we would say prove the logically equivalent contrapositive instead of the original claim. This implies the original claim holds. So if we want to do this example, we will take the same proof we did for the direct proof up here. We're going to start with a contrapositive here, right? We're going to say if x is an odd integer, this implies 3x plus 2 is also odd. So if x is odd, this means we can write x equals 2m plus 1 for some m that's an integer. Therefore, if we start with 3x plus 2, this is the same as 3 times 2m plus 1 plus 2. Distribute the 3, we can see we get a 6m plus 3 plus 2. We can regroup this a little bit. We could say we have 6m plus 4 plus 1. Factor 2 out of this piece here, we can say we have 2 times 3m plus 2 plus 1. And as m is an integer, this implies 3m plus 2 is also an integer. Therefore, we know that the 3x plus 2 is an odd integer. So what this tells us is if we assume x is odd, it guarantees this 3x plus 2 must also be odd. So if we're trying to show that 3x plus 2 is even implies that x is an even integer, then we know that x can't possibly be an odd integer because we would get an odd result to begin with. It violates our original assumptions. Now the next one we're going to do is we're going to talk about proof by contradiction. It's similar to our proof by contrapositive. With the proof by contrapositive, you're just reframing the original question to directly prove the contrapositive. But with the proof by contradiction, what you're going to do is you're going to assume the conclusion is false. Then show this assumption leads to absurd results. So the classic example for this is going to be the example we do. If you haven't seen this in a proofs course, then we'll see it now, but this is one of the most famous examples of a proof by contradiction. We want to show the square root of 2 is irrational, i.e. square root of 2 does not equal m divided by n no matter which value of m you pick out of the integers, and whichever value of n you pick out of the integers that does not include 0. So what you might do is you might say, well, assume square root of 2 is rational. This implies square root of 2 equals m divided by n for some m, that's an integer, and for some m that is a non-zero integer. And we're also going to assume that m divided by n is fully reduced. So these two numbers will be relatively prime. You can't cancel out anything from the fraction. What we might do then is we might be able to say, if this is true, we can certainly square both sides. 2 is equal to m squared divided by n squared. And then we can bring the n squared over. We get 2n squared is equal to m squared. So what does this tell us? This implies that m must be even. Because if m were not even, then we wouldn't be able to have these two things be equal. We have 2 times the integer squared is still an integer, m must be even. So now what can we do? We can say this implies m is equal to 2k for some other integer, k. And we can rewrite this equation now as 2n squared equals 2k squared, which gives us 4k squared here on the right-hand side. And if we were to divide both sides by 2, we now see n squared equals 2k squared, which also implies that n is even, which implies n equals 2, we'll use a different letter. We already used k. We'll say p for some p in z. But this is a contradiction, because this means n and m share a factor of 2, and m divided by n is not fully reduced. So then we would state, thus, to avoid contradiction, the square root of 2 is irrational, because if it were rational, we would run into this contradiction of the contradiction with the relatively prime part. The last method we're going to talk about today is proof by induction. So how does this one work? You're going to have 2 steps to this one. First step, prove the base case. So the base case, typically you're going to assume n equals 0, but it could be different. It could be n equals 1, n equals -1, but it's going to be some integer value, and it'll be clear based on the context of the problem. Then the second case, you're going to assume the claim holds for all 1 less than or equal to n less than or equal to k. You can pick k whatever you want to. You could say strictly less than rather than less than or equal to. These are all logically equivalent. I'm going to state it this way. Some people swap the k and n, and we'll state it clearly before we do this step anyways. If you assume this is true, though, you need to show this implies that the claim must also hold for k plus 1 is when n is equal to that one. So the example that a lot of people give is you can imagine an infinite ladder. It starts off on the ground, but it keeps going up and up and up forever. So you need to show the first rung is true, the base case. And then you need to show if you're at any given rung, maybe you're at this rung right here, you can always take another step upwards. And that's enough to show that the ladder continues on forever. So for our example, we're going to prove a nice formula about the triangular numbers. So suppose we have the sum 1 plus 2 plus 3 and plus 4 and so on. You just keep summing up and up and up and up. You might ask the question, well, is there a nice formula you can set this equal to? And it turns out there is. The nice form for this is you can take n times n plus 1 divided by 2. So how might we prove this? Well, the lowest possible n we could use would be 1, because that's going to be the formula where we sum up only the first term, the 1 all by itself. So to show this, we get 1 on the left side. We might state clearly base case n equals 1. Let me just make sure we're clear. We're going to show this thing right here. So the base case, we set n equal to 1. On the left side, we get 1. On the right-hand side, we get 1 times 1 plus 1 divided by 2. 1 plus 1 is 2, so we get 2 over 2, which is equal to 1. Base case checks out. Now for the inductive step, we need to state this part clearly now. Assume the formula, you might say the claimant set here, the formula holds for all n such that 1 is less than or equal to n is less than or equal to some fixed value k. So what is this going to imply? This implies the sum from I equals 1 up to k of I must be equal to k times k plus 1 divided by 2. If I want to make the sum go up to one more value, I could add k plus 2 to both sides, so I could say, or k plus 1 to both sides rather, so we get k plus 1 over here, plus the sum from I equals 1 to k of I, and this is going to be equal to the sum from I equals 1 to k of I still, but instead of having k up there, we're going to get k plus 1. What about on the right-hand side? It's still equal to the right-hand side. We got k plus 1 divided by 2, but now we add an additional k plus 1. So if we wish to factor this up appropriately, then what we might do is we might factor a k plus 1 out of both terms, giving us k plus 1 times k over 2 plus 1. Now from this k plus 1 times k over 2 plus 1, we can rewrite the 1 as 2 divided by 2, giving us k plus 1 times k over 2 plus 2 over 2, which gives us k plus 1 times k plus 2 all divided by 2. And because we have this piece right here, which is indeed equal to this piece, we've shown that the inductive step is also true. So then at the end of a proof, we would probably want to be careful to state this rather than putting a box earlier like we did. That was bad practice on my end. Even though we did the necessary steps, it's a good idea to just state your conclusion. As the base case and inductive step hold, the claim must hold for all n greater than or equal to 1 by induction or something. Just make sure you're stating that you're using proof by induction. That's good enough. You did the proof. And some of the style and kind of habits come into play later. As you get further on, you usually don't want to be quite as formal, but it's still a good habit to get into. So for the purposes of the class, I'd like you to be this formal for now, and certainly for this first assignment when we're reviewing these kinds of proof methods. I hope this is helpful. That's all.